This is the first video on fuzzy logic control method. In this video, we will go through the fundamental concept or idea of fuzzy logic. We will start by learning what the name fuzzy means, then move on to the concept of fuzzy logic. Consider the following scenario. I am driving a car from point A to point B at 80 miles per hour. If the distance between points A and B is 160 miles, it will take me 2 hours to travel that distance. These quantities, that is 80 miles per hour, 160 miles and 2 hours, are all precise or crisp quantities. Crisp values or quantities tell us that if I travel from point A to point B at around 80 miles per hour, I will cover the 160 miles in exact 2 hours. But in reality, it depends on the traffic situation, the road surface, environmental conditions, that is if it is snowing or if there is a sandstorm. So in reality, if I am traveling from point A to point B and there is no traffic, it will probably take me around 2 hours to get from point A to B. If there is light traffic, it may take 2.5 hours. If there is a heavy traffic, it may take 3 to 4 hours. If there is a lot of traffic, it will take a long time. These are not really exact statements. About is a vague term. How long is long and how short is short. These statements we regard as imprecise or fuzzy statements. Starting with expert systems is the best method to introduce the concept of fuzzy logic. In the context of control, an expert system is a computer software that mimics the behavior of a skilled operator. For example, suppose you were driving a car and needed to keep a certain distance between your car and the car in front of you. If the car in front of you slows, you must apply the brakes. If the gap between your car and the car in front of you is shrinking quickly, you should hit the brakes more forcefully. You no longer need to model the car engine, drivetrain, or inertia to accomplish this. You know from experience that if the distance between your car and the car in front of you is shrinking, you should apply brakes proportional to that shrinkage. Distance is one variable in this example, while the rate of change of distance is another. Your actions are based on these variables, and when you apply the brakes, you don't think about the engine model. You do it instinctively. Similarly, most processes in real life are controlled by skilled operators. Therefore, rather than modeling the car, we model the driver or experienced operator in an expert system to design the control for a system or process. Someone might wonder why expert systems are needed in control when we can design the system's control using its mathematical model. The answer to this question is that designing control for a system using a mathematical model of that system, such as a car engine, drivetrain, or other system, is not only time-consuming but also difficult to obtain in many cases. And even if it is obtained using some method, it contains errors and is affected by disturbances. Furthermore, many people lack the level of mathematical knowledge required to effectively model the system. Therefore, expert systems are used in control, in which rather than modeling the system, we model the behavior of operator. So to summarize, most complex processes are controlled by human operators. Expert systems, rather than modeling the plant or process, capture the behavior or instincts of operator. I will explain this by considering an example which contains a mixing tank. We measure the temperature of the tank to keep it at a certain value, for example 50 degrees centigrade. To do so, we have steam flowing into the heat exchanger. If the temperature of the liquid in the tank is very low, we increase the flow of steam, which exchanges with cool liquid in the mixing tank, and its temperature rises to the desired value. When the temperature reaches the desired value, we close the valve. In this video, we will discuss two methods of control, that is crisp control and fuzzy logic methods. And through this simple example, we are going to implement crisp control and fuzzy logic methods. Let's start with the crisp control method. If my preferred temperature is 50 degrees, I may say that anything below 50 degrees is cold and anything beyond 50 degrees is hot. If it is cold, we will fully open the valve, and if it is hot, we will fully close the valve. This is similar to our relay controller in that it has an open-close operation. These two simple statements can also be used to express this control action. If T is less than 50, then valve position is 100% or fully open. Otherwise, if T is greater than 50, then valve position is 0% or fully closed. The disadvantage of such a controller is that the temperature of the tank will oscillate around 50 degrees in steady state and will not settle to a fixed value, causing the mechanical valve to wear out prematurely. To eliminate the oscillation, one method is to divide the tank's temperature range into tiny areas. For example, I can choose the 45 to 55 degrees range as the acceptable range or the OK range. The small positive region runs from 55 to 65 degrees. Medium positive region ranges from 65 to 75 degrees, while large positive region ranges from 75 to 85 degrees. Similarly, the 35 to 45 range represents a small negative region. Medium negative region ranges from 25 to 35 degrees, whereas large negative region ranges from 15 to 25 degrees. In this way, we have developed a more sophisticated control strategy, in which the valve remains in its current position if the temperature is within the desired range. If the temperature is small negative, open the valve by 1 degree. If the error or temperature is medium negative, open the valve by 2 degrees, then 3 degrees, and so on. Close the valve by 1 degree if the present temperature is small positive, that is, the tank's temperature is little higher than the required temperature. Close the valve by 2 degrees if the error is medium positive, and so on. So minus and plus refer to how far the valve is closed or opened. Minus sign refers to the valve being closed, whereas plus refers to the valve being opened. It can also be expressed in if-then statements. In previous case there were only 2 statements, but this case has many statements. In the whole discussion, our controlling variable is action on mechanical valve. The question now is, where does this action originate? For this, I ask the operator, that is, what are you going to do if the temperature is about 50 degrees? He will say, I am going to leave the valve alone, implying that the temperature is fine. But what if the temperature is between 55 and 65 degrees? He will say something like, I am going to close the valve by 1 degrees or minus 1. What if the temperature is between 35 and 45 degrees? He will say, I'll open the valve by 1 degree, that is plus 1. Crisp control refers to the fact that each temperature value belongs to only one subdivision. For example, 69 degrees is a medium positive number and belongs only to this region. By managing the degree of opening and closing of the valve, rather than totally opening or closing the valve, we may reduce the oscillations of the mechanical valve. This method is better than the relay controller method, however, it has a flaw. We will use an example to help us understand this. The temperature of 24.9 degrees is in the large negative range, indicating a plus 3 action. Similarly, the temperature of 25.1 degrees is in the negative medium range, and the action is plus 2. So under crisp control, our controller will perform 2 different actions for 2 similar temperatures. But if you ask an experienced operator what he would do at these 2 temperature values, he will tell you that these are the same temperatures and that he would only recommend only one action for both of them, perhaps plus 3 or plus 2. Although the crisp control method has minimized oscillations when compared to the prior scenario when the valve was fully opened or closed, oscillations will still be significant when temperature enters from one region into another due to rapid changes in control action. This problem arises because each temperature value corresponds to only one region. Fuzzy logic is a better technique for reducing mechanical valve oscillations. Each temperature value in fuzzy logic may belong to one or more than one regions rather than only one, as in crisp control, which is why it is named fuzzy. Now let's have a look at what fuzzy logic is. We can also represent the previous crisp division like this in the form of crisp or rectangular membership functions. Crisp membership means any temperature value belongs 100% to one particular division. Therefore, each temperature has membership value of 1 in crisp control method. What we have learned so far is that how to implement expert system in the controller using crisp membership value. For understanding fuzzy logic controller, consider the triangular membership functions. In the triangular membership functions, the temperature of 30 degrees belongs 100% to the medium negative region, whereas the temperature of 38 degrees belongs 20% to the medium negative and 80% to the small negative regions. Consider the case of two temperatures that were very near in values, that is 24.9 and 25.1 degrees. The temperature of 24.9 degrees belongs 49% to the medium negative and 51% to the large negative. Similarly, the temperature of 25.1 degrees belongs 51% to the medium negative and 49% to the large negative in fuzzy logic controller. In crisp control method, if the temperature reading is 25.1 degrees, the operator would open the valve by 2 degrees. If it is 24.9 degrees, the operator would open the valve by 3 degrees. But under the fuzzy logic method, how do we calculate the action value of the valve for 24.9 degrees and 25.1 degrees, which fall into two regions? To do so, we multiply the crisp control actions value by the membership value of the triangular membership function. For example, control action for 24.1 degrees would be 0.51 times 3 plus 0.49 times 2, which equals 2.51 turns. Control action for 25.1 degrees would be 0.49 times 3 plus 0.51 times 2, giving us 2.49 turns. Actions under crisp control were extremely different, that is 2 and 3. However, actions in fuzzy logic control are similar, that is 2.51 and 2.49. Triangular membership functions, in contrast to crisp or rectangular membership functions, give us identical actions for similar temperatures. So what exactly does fuzzy mean in this context? In this case, fuzzy means that we enable the temperature to belong to two regions or groups instead of just one, with each group's membership value. For example, 24.1 degrees has two membership values, large negative 0.51 and medium negative 0.49. These membership values were calculated here by intersecting vertical lines with triangular straight lines solely for the sake of analysis. Computers are used to find membership values in practice, as they are difficult to find analytically. We were able to solve the challenge of very different control actions for similar temperature by using fuzzy membership functions, without increasing the number of rules and if-then statements. As a result, control action varies smoothly in response to temperature variations, resulting in minimal oscillations around the whole operating range. So far, we have considered only one variable to decide the control action value, that is temperature of liquid in the tank or tank temperature. While in practice, plant operator may use different variables to decide the value of control action. Now we will discuss an example in which two variables are used to decide control action. We assumed in the previous discussion that the temperature of liquid pouring into the tank remains constant, but in reality it may vary on different days depending on external conditions. As a result, if the second variable is the temperature of the liquid flowing into the tank or the inlet temperature, the operator may make different valve adjustments than in the previous example. If the inlet temperature is generally 15 degrees, but it is 25 degrees today, then less steam is required to raise the tank temperature. As a result, the operator can adjust the valve settings for each region as needed. For example, if the temperature is OK, the valve position remains unchanged. If the temperature is small negative, open the valve by plus 0.5 degrees as opposed to plus 1 degrees in the preceding example. It is plus 1 degree for medium negative, whereas it was plus 2 degrees in the preceding case. If the current inlet temperature is 5 degrees, then more steam is required to raise the temperature of the liquid in the tank. As a result, the operator will alter the operation and increase the valve settings as seen here. Because we now have two variables, namely inlet and tank temperatures, as a result we must merge the rule bases of these variables to create a two-dimension table. To use fuzzy logic to calculate the value of a control action, we must first establish the crisp control values for these two variables. To illustrate how this 2D table works for crisp control method, suppose inlet temperature is 5 degrees and tank temperature is 30 degrees, so the action would be to open the valve by 3 degrees. If inlet temperature is 25 degrees and tank temperature is still 30 degrees, then action would be to open the valve by 1 degree. Remember that we are using crisp membership values to calculate the control action of valve, and the problem with crisp membership values is the same, that is, for similar temperature values, the control action is drastically different, causing oscillations when the temperature value moves from one region to the next. We will employ fuzzy triangular membership functions to tackle this problem. For tank temperature, we utilize the same triangular membership functions as in the previous case, but for inlet temperature, we separated the entire region into cold, normal, and hot regions. To put it another way, a tank temperature of 30 degree means 100% medium negative, 50 degree represents 100% OK, and 70 degrees represents 100% medium positive. Similarly, a temperature of 15 degrees is considered normal. A temperature of less than or equal to 5 degrees is considered cold, and a temperature of 25 degrees and greater is considered hot. The temperature in the middle has a fuzzy membership values. It was simple to decide control action value when inlet temperature was constant and these two rows were absent. For example, control action for 25 degrees is equal to 0.5 times 3 plus 0.5 times 2 or 2.5 degrees. When we have two variables such as tank temperature and inlet temperature, the challenge is figuring out how to integrate these two temperatures to create a single control action value. Consider the following scenario. The tank temperature is 64 degrees, which falls into the medium positive and small positive regions, and the inlet temperature is 12 degrees, which falls into the cold and normal ranges. So part of the table we need for these two temperature values is the intersection of these columns and the two rows, that is these four cells. 64 degrees has 60% small positive and 40% medium positive membership values, while 12 degrees has 30% cold and 70% normal membership values. We can also present it in this manner. So each cell has two membership values, and the difficulty is figuring out how to combine them into a single control action value. There are several approaches for solving this problem. However, we will choose the intersection or AND method, often known as minimum weight method. In this method, we look at each cell individually and multiply only the minimum membership value with the crisp control action value of that cell. For example, the minimum membership value for the first cell is 0.3. So we will ignore 0.6 and multiply 0.3 by the crisp control value, which is minus 0.5. Then we add all of the products together and divide by the sum of membership values considered for each cell. The resulting control action value is minus 1.1562, which indicates that the valve should be closed by this number of degrees. Now I'll explain some keywords related to the fuzzy logic. The first keyword is fuzzification, which is a process in which crisp quantities are converted into fuzzy quantities. Here fuzzification was done when we converted crisp membership values of tank and inlet temperature into fuzzy membership functions or quantities like hot, cold, medium, positive, etc. Fuzzy quantities do not always belong to only one group or region. They may belong to two or more groups or regions by some degrees. As a result, the topic of how to choose fuzzy membership functions arises. To choose fuzzy membership functions for a particular process, you should be familiar with the system or process before dealing with that system and have some experience with it. Then you build membership functions for that system based on your intuition and experience. Take, for example, the membership function for motor speed. Here, a speed of less than and equal to 500 is recorded low, while a speed of greater than and equal to 2000 is considered high, while a speed of 1250 is considered normal or medium. So how did I judge whether a speed is too fast or too slow? Because I understand how a motor works and what speed is considered normal. All of this is based on intuition and experience. The second keyword is rule base. It is a knowledge-based lookup table which contains crisp value of control action. These values also come from experienced engineers and operators. The third keyword is inference mechanism. This mechanism is simply called if-then statements. It contains all rules or if-then statements for a particular process or system. For example, one if-then statement from the previous examples is: if tank temperature is small positive and inlet temperature is cold, then crisp value of valve position is minus 0.5 and membership value is minimum of 0.6 and 0.3. The last keyword is the defuzzification. It is a process of combining all if-then statements outputs to get a value of control action. In simple words, fuzzy variables are converted back to crisp quantities in this process. Different methods are used for defuzzification process. We use the center of gravity method in the previous example. This method gives us the crisp value of control action by using this formula, in which mu is the minimum membership value against each cell and B is the crisp value of control action of that cell. U is the overall control action value. This was the first lecture on the idea or concept of fuzzy logic. In the next video, I'll show you how to use MATLAB to implement fuzzy logic control. If you liked this video, then hit the like button and please subscribe to my channel. See you in the next video.